We're going to be seeing it all. And then, of course, you can't forget your protein drink. Very nice.
Yeah. I like your life advice before presentation.
It's
Yeah.
very important to stay hydrated, caffeinated, and protein saturated.
Bon. Um, well, it's 9 a.m. Hi, everyone. Welcome for this third day of our seed seminar series. Today, we will tackle more on the how basically we use remote sensing for figuring out where we produce and like when we produce agriculture, and are we able to estimate the area of the our production, and then are we able to estimate the productivity and at what extent. And then by the end, we select two type of productivity at the yield aspect, and then we will see also the ecological productivity. And by the end of the presentation, we will do a live demo with the 6 grain team that they will be telling us more about how they basically use the scientific methods operationally and in industrial setting to answer the needs of their clients. So now we will start with Dr. Christian Abys, who is a postdoctoral researcher in NASA Harvest. He will tell us more about how he does wheat area mapping and land use, land cover change in, and sometimes in places where he doesn't even have um, field data. So the floor is for you, Christian. Thank you.
Thank you, Waleed. Hi, everybody. So, thank you, Waleed, so much for inviting me here and for introducing me. So, I'm a postdoctorate research associate in NASA Harvest, and my main area of concern is wheat area mapping, agricultural mapping, and particularly in Eastern Europe. That includes Russia, Ukraine, and Kazakhstan. So today we're gonna keep it kind of high level, but I'm gonna keep it interesting. I want to go into just really different kinds of wheat mapping. And then more importantly, I want to get into more about how we actually use that data to make um, informed estimates, informed projections, and kind of like the minutia in between that sort of stuff. So if you have any questions, please just feel free to put it in the chat and I'll stop and we can talk about it or however we want to do it. But let's get into it. All right, so very interesting. I kind of wanted to start this off. And I found this out like a year ago and thought that was actually kind of interesting. But one of the first use cases for agricultural mapping and kind of making this go full circle with what I do is was the Landsat 1 mission, which launched in 1972. And one of not it's not the sole reason, but one of the major reasons why they did this was they wanted to actually monitor Russian agriculture or Soviet agriculture in the early 1970s. So it's kind of interesting how today we're going to be talking about that as well, talking about Russian agriculture, why it's important, and the kind of the new stuff that we've been doing with it. And so if you were in the webinar yesterday with Leo, I'm very close colleagues with Leo Shmilo, and he kind of gave a global view, and so now what we're going to be doing today is we're going to be looking more at a more closer inspection of how we can, use these change detection maps to make informed guesses. So why monitor it? Now I know this was covered yesterday, but I want to get a little bit more into maybe more specifically why monitor it in certain countries. So it is one of the largest staple crops in the world. When we talk about remote sensing and how we view things, we need to kind of think of ourselves as looking at it from a bird's eye view perspective, right? And so what does that mean? It means we tend to separate different kinds of crops into categories, as in wheat, corn, maize, or corn and maize are the same, rice, for example. But we also can look at it in terms of coarse grain, soft grain, winter cropland, winter wheat, spring cropland. And I'm going to be throwing a lot of these terms around, and some are interchangeable and some fall under the same umbrella terms. And it really depends upon how you pull apart and inspect the data that you're looking at. And so in the specifics for Russia, and we'll get more into it in later slides, it's a very large country, one of the largest. It has a massive agricultural industry, and that agricultural industry in the past 30 years has changed significantly um, since the fall of the Soviet Union and going into the 21st century. There's a lot of peculiarities and a lot of really interesting things that have been going on there. And as we all know, there's a massive geopolitical change going on with the war in Ukraine, and not a lot of information is being released and about what's going on there in a place that is essentially, Ukraine and Russia combined, exporting roughly 25 to 35% of the world's wheat. So taking that into context, when you look at a market, you look at how people um, rely on food supply chains. 35% exporters, 35 places that export 35% of the world's wheat um, has significant implications on the market itself, the world global trade market, which then has implications on food security and food supply. So this is a major reason why or why I and my team and as a Harvest, focus so intensely on this kind of work. Um, yeah. And again, as we talked to, as Leo mentioned yesterday as well, um, we can also use these things for, using these kinds of maps and classifications and analyses to as a proxy for quantifying climate change, right? So there's a ton of data, right? Atmospheric scientists, physical scientists, all different kinds of avenues and perspectives you can look at for both measuring climate change, but then measuring the impact. And what we do with our lab, with NASA Harvest, and then at University of Maryland is we use agriculture as another way of understanding climate change. And we can use it as both a way to quantify it and then also as a way to see the impact of it. And this is a really, really interesting way of quantifying these kinds of changes. So keep all of that in mind. So again, we have food security, we have trade, so money, and then we have quantifying climate change, which has both ways of understanding it and then ways of also measuring its impact on agriculture itself. All right, so first thing I want to get into, and I'm gonna kind of be a hardo about this one. So for the people here who are listening, who are researchers, who are wanting to get into remote sensing of agriculture, um, or if they do in the private side as well, one of the single most important things about remote sensing is ground truth and statistics, and they can be used either or interchangeably. Why? So when we look at the world um, with satellite imagery, with Earth observation data, we're looking at it from a bird's eye view perspective. And if we want to quantify the things that we see, we want to be like, okay, this is that and that's that from what we see from the sky because it's a completely, new perspective. We need ways of relating that information to what we see in the ground. And we need lots of it. And that comes in the form of both two things, statistical information. So that's information provided by the country, provided by a non-governmental, NGO such as the FAO or the USDA, Foreign Agricultural Service, ESA, NASA, places like this, providing information about, how much wheat did this place produce per year? What is the cropland area? What was the land abandonment? Where? How much? Um, these things are incredibly important because when you're producing your maps and you're producing your estimates, you need to do um, historical classifications and observations to then validate what you want to see in the future. So without this, if you produce something, you go, okay, I don't know, I don't know what it is that I'm looking at. I don't know how well it is. I don't know what the performance is. And then the other side of those things is ground truthing, right? So in this term for ground truthing, there's many different ways to think about it, but when I say it, ground truthing is points on the ground, i.e., I have a point that's geo-coordinated to a winter cropland or a winter wheat farm. This says that, okay, I can then use this information. I can use these points for this winter wheat, winter barley, spring barley, sunflower, and say, from my satellite, I know that this is this because it was recorded on the ground. Now, in my specific case, for the work that I do with Russia, I cannot go to Russia and collect GPS coordinate points of different crop fields, different farm fields. I do this in Kansas when I go there, and you're literally driving in a car and you just look out the side of the window and go, this is, wheat, corn, maize, forest, river, things like that. Can't do that in Russia. Another thing can't do in Russia is have ever since the war happened, I cannot have, or I can kind of, we have ways of getting direct primary source information for the kind of their agriculture production. Ever since the war, they've stopped sharing that information, which adds another layer of complexity and hardness to how I can actually validate what I do for my work. And so what I do for my work is I forecast Russian wheat production for the year, reproduction, both winter and spring, and then also summer crops as well. So to do this, I have a lot of historical information. I go online, I look at third party sourcing, I try to see what they're saying, and I build out these very large Excel sheets of all the information that everyone records. And I look for discrepancies in the data. And I look to see who's right, who's wrong, and then I match it up with my information that I get from the maps that I produce, which I feel and which I know is, direct observable information, right? That's science. So we take all that information and I take all that information, I try to mash it all together and make sense of it. So if there's one thing you can take away from this lecture is ground truthing and statistics is king in remote sensing. Okay. It also dictates the kind of modeling that you do as well, but we'll get more into that in a second. Okay, so today we're going to be talking about two different kinds of forecasting, and I will share examples of both and case studies of both that I do with my work with NASA Harvest. So we have both in-season forecasting and we have interseasonal forecasting. Now, in-season forecasting, as we all, I think we all can wrap our heads around is we are making a forecast using within the crop's growing season. So starting when the crop is planted towards when it goes into senescence and harvested, I'm making observations using satellite data. I'm building maps, and then I'm validating those maps with points, with sample points. Um, and I'm getting closer and closer to what I feel is a correct estimate as the time goes forward. So that means, removing uncertainties, removing uh, getting a better observation, getting a better time series, a longer time series of that crop as it grows throughout the season, and then making an informed guess or an informed estimation based on the areas that I produce. Now, an interseason forecasting is a little bit more nuanced and it has a lot more caveats to it. And that's going to be for, what's going to be next year's area estimation. What's going to be in the next 5 years, the next 10 years, the next 20 years? What can they produce? And this has to do with land capacity, right? So how much land do they physically have? How are they using that capacity, using that land? Policy scenarios, inputs such as fertilizers, maybe even oil prices. Oil is used to make fertilizers in many cases. And then lastly, also climate change, which is we'll get into in a second with Russia specifically, because there's lots of implications about climate change. And then on the third note, just want to say, so what is pixel counting? So we don't ever want to have, you could if you were doing a quick and dirty, but really you should not, is pixel counting is when you produce a map, right? So you classify all the pixels in your raster data of your received region, and you count all those pixels up and then you just say, okay, and then multiply it by the spatial resolution, and then that's your area estimate. That's not what we do for area estimation. We produce the map, we get the pixel counting, but we then sample that map and we sample for its accuracy, i.e., in our case that we're going to be looking at today, winter cropland or not, or winter wheat or not. Once you get that, you build a confusion matrix, and from there you can then say, okay, I this map is 90% correct, 95% correct, or I'm missing here, I'm correct there, and then you get your final area estimation. I'm going to do that through stratified proportional random sampling or two-stage stratified sampling. I know that Leo covered that yesterday. And this is all derived from both Steinman et al. And Olson et al. Two papers that, and I'll link those later on, two papers that every remote sensing person should know if they're getting into land cover and area estimations, things like that. So, all right. Now, before we get into more of the fun stuff, let's get into one more thing I wanted to cover, which is data requirements and scale. Now, a lot of times, and I've learned this over my years of doing this, people want to get into, make the most pretty maps, the most beautiful maps, and I love making beautiful and pretty maps. It satisfies me deeply, um, as you can see. But sometimes, you need to think to yourself before you start a remote sensing campaign, before you get into, you know, building out your architecture, your pipeline for how you want to handle data, you really need to think to yourself, what is the end goal of what I'm trying to do? What is the end? What would satisfy it to be a mission success for your project, right? And so you need to think about these things before you get into it. So imagine for yourself, you want to build a map of agriculture of subcrop types in Russia. If you were to build a map at a 10-meter resolution of Russia, Russia's a huge country. 10-meter pixel resolution for the entirety of Russia for multiple years, for example, is a lot of data. Now, it's not saying you can't do it, and I do it sometimes for certain mission needs, but you can get this, you can fulfill your mission criteria using coarser resolution data, especially in terms of mapping large homogeneous crop types, such as winter wheat for this example. Same thing that goes, for example, in Kansas. Kansas is a very large state. It also has a very homogeneous um, monocrop type, which is wheat. And so if you wanted to build out a map of wheat in Kansas, for example, or a map of wheat in Russia, especially for Russia, 250-meter, even though this map on the left looks kind of messy a little bit, it'll still arrive. If through two-stage stratified sampling, proportional random sampling, you will more or less arrive uh, at the same answer or conclusion of, i.e., how much wheat do we have, or how much wheat was planted this year or being harvested this year. So I want to always keep that. You should always keep that in mind too. So what we have so far, we have what kind of forecasting am I using? Um, what kind of ground truth or statistical data do I have? And lastly, what are the data requirements that I need to actually fulfill a successful mission for an area simulation for my, for the region that I want to do this in. I would always push for, if you have a very large region, big country, you could do the 250-meter first. You create that mask, and then within it, you can then do it. You can do a much finer resolution a much finer resolution satellite data, so that you actually reduce the amount of data that you're actually classifying within your either deep learning model or your GMM model, what have you. And just for a heads up, so on the left, with the MODIS data, it was created using a GMM Gaussian mixture model with MODIS. And then on the right, we have a Sentinel-1 and 2 produced map with an LSTM, long short-term memory deep learning model from TensorFlow. All right. So let's get into in-season forecasting. Now, there's just like with Modus, there you can do in-season mapping forecasting, right? Because forecasting, we're making an inference for the end of the year product. You can use both for in-season mapping, and I tend to use both sometimes, or that does make sense. I use both. I use both sometimes. I usually will start with Modus first, just to get an idea because it's fast. It's important in classifications to have high amounts of iteration because you can build the map and then you can look, just literally physically look at it and go, does this look right? Is it looking weird? Am I, way off? Am I way under? Um, then you can iterate and improve yourself quick. If it takes 7 days to build a 10-meter map of Russia, if you mess up, you got to take another 7 days to build it again. And in the world of forecasting, you want answers quick and you want them to be right and you want them to be verified from previous years. So this is kind of what it looks like, or this is what it looks like when you do using a deep learning model for winter cropland detection using Sentinel-1. This is actually just Sentinel-1, by the way, which is pretty interesting. So it's just radar for mapping winter wheat in Russia, right? And so you can see as the year progresses, right? So winter cropland, winter wheat planted in the fall, goes dormant in the spring or in the winter, and then has a quick rise up in the spring, and then it gets harvested in like late May, early June, or mid June. And you can see how the map gets more and more filled out as you progress forward. And what was interesting from this actually, and this is a paper I published, was you can really actually capture a lot of that planted winter wheat area very early in the season in the fall planting area using solely radar data. And why radar data? Why not use True Color or Sentinel-2 or whatever? Well, the biggest challenge for agriculture forecasting is clouds, right? So if you have a cloudy image, if you're using True Color, if you're using Sentinel-1 optical observations, clouds will, you have to composite, make longer and longer composites to actually, get a cloud-free imagery. And with radar, you don't have that problem. So with radar, you can, get really consistent data consistently, and you can build out short window composites over many times, and then be able to make predictions every week or 2 weeks or what have you. Um, and but this is the same principles for optical remote sensing as well. Pretty interesting stuff. So again, yeah, this is in-season forecasting, right? And with a Gaussian mixture model, which is taking only a single feature, this is taking multiple features. So every 2 weeks, it's adding on another feature to have a prediction be made on. With the Gaussian mixture model, you're only using one feature, which is a NDVI difference. And if you're interested in that, I can just shoot me a message and we can talk more about it um, going forward. Outside of this, it's a lot to get into. All right. Anyways, so yeah, so this paper I wrote about, it was published in Science of Remote Sensing recently, and it has a lot to do with using Sentinel-1 and in-season mapping to make really cool, really accurate predictions every single year. Because if you have a cloudy year, then you can't make a good prediction, or will take longer. All right, so let's get into some more of the cool stuff that I've been doing over my PhD and continuing now forward. So when I was a PhD student, very early, we were looking at statistics for a lot of different countries. And I saw for Russia, just looking at their statistics, what they, coming out every single year, this is how much we produce, this is our cropland area, this is our yield. I saw that in the past 20 years, they increased their production of winter wheat by 267%. That is an insane amount of growth, right? Most countries over 20 years, 30 years, with the advent of new technologies and all that kind of stuff, 10, 20, 30%. That's, pretty significant, but 267% is an insane number. And I actually went to the agricultural professor um, at my school at UMD, and I brought this up to him, and he looked at me and he was like, "Nah, they would never do that. If they wanted to plant winter wheat back then, they would have done it, and this is doesn't make any sense." And I was like, as a remote sensing person, I was like, "Oh, well, we can prove this, or we can see what's going on. Maybe they're lying, maybe they're what's going on." Um, and that's what I did. And I built 3.5 years of research on this almost this single statistic of how does a country as large as Russia increase their winter wheat production by 267%. It's a pretty wild number. So the first thing that we wanted to get into as a land use research scientist, right? So kind of wear different hats sometimes, is you want to, remote sensing is not just about satellite information. I know that's crazy, but hear me out. As a remote sensing scientist, as a researcher, as somebody who's passionate about these things, you always, and going back to ground truth and statistics, you want to always be thinking about what is happening on the ground so that you can make interesting and thoughtful analyses from what you see from the sky or from space. So we had three things going on in Russia in the past, 30 or so years, that could have led to this kind of growth, right? We have post-Soviet land abandonment. So after the Soviet Union, bureaucracy collapsed, things had to be reorganized in how people own land, XYZ. We have the second one being the national security strategy, this huge document that Russia produced about how they were going to strengthen their wheat industry. And then the third one, which is many people have been curious about, and in 2010 and 2005, um, people were starting to try to answer this question of, okay, well, if we have a warming climate, if we have a changing climate, a shifting climate, how is that going to impact countries in the northern latitudes and how they grow food? Because we can see that from observations of temperature that temperature is increasing. And you would think to yourself, well, you know, if it's getting warmer, then maybe winter climate change would, positively impact agriculture. But, there's, winter wheat specifically is an amazing tool or proxy for understanding climate change because it takes three different seasons of climate regimes to grow. And in the winter, especially in the winter, you actually want snow coverage on top of winter wheat, because it does two things. One, it acts as a thermal insulation. So if you ever tried to grow like a fig tree, I know this is a weird example, but like my father would grow fig trees, and if you don't insulate it, wind will draw out the moisture from the tree itself in the winter. And so you actually want snow on top of winter wheat during its dormancy period to cover it from wind that could blow the crop and make it dry and kill it. We call those winter kill events. So if you don't have snow, not good. Second of all, if you have snow and then it melts in the spring, it acts as a nice booster to moisture content in the soil, right when it starts to come out of the winter period. So, and it's another secondary advantage. So really the question is, what am I trying to say with this? The question was up in the air, is climate change really impacting in the southern regions where it's already warm and already advantageous to grow winter cropland or winter wheat? Is it a good thing and what's happening? So before we get into the analysis of it, this is what we did, or what I did. We built 20 years or 8 years of 20 years, but we used 8 years of winter wheat maps. And in this case, we're just going to be concerned about the winter wheat portion of the classification here using MODIS. And this is the uh, western portion of Russia. And around here is their main, super highway for growing winter wheat, right? Ukraine is here, and then we have Russia. And this is probably, maybe India is close as well, but this is probably the largest concentration of winter wheat growth in the world. Um, Also Kansas as well. But really, this is a very, very important area of the world for growing food. All right. So we took these maps, and we have them all here, and we stacked together 4 years for 8 years in total. So we have two stacks, right? And this is the land cover land use change portion of this talk. And so we stacked those years, and if they had winter cropland for a pixel, then we would mark it as, if it had it for 2 years, that pixel would contain a two. If it had it for 3 years, a three. And we did that for both intervals. We then stacked it all together, and we threw points based off of that both how that winter cropland area changed in terms of, okay, well, in the previous year and the previous interval, 2001 to 2004, it had no winter cropland, for example. And then in the second interval from 2017 2020, it had two winter cropland detections. And so that was expansion. Now we also have intensification. Now, for people who don't farm or are unfamiliar with it, so usually what you'll do in farming is you'll have a 1 year where the land will remain fallow to regain nutrients, to regain nitrogen in the soil. And then the next year they'll plant a crop, for example, winter wheat or corn or rice. And then that's a cycle. And then the next year they'll go fallow, and then the next year it'll be another crop, for example. So we have expansion, which is where there was no crops, no winter cropland being planted. And then in the second interval, there was winter cropland. And then we have intensification, where there was, let's say, out of 4 years, one winter cropland. There was winter cropland for 1 year. And then in the next interval, there was two, three, or four times winter cropland was being planted. And why is this important? This is important because ultimately, we wanted to see what is the future capacity, i.e., the intra-seasonal forecast or projection for how much more this country can keep up its rate of growth over the past 20 years, right? Again, remember that 267% growth we had. We want to know, can they keep growing like this? Like, is this, how much more can they keep adding to their production? And on another note, I just want to say before I go into this, another reason why we wanted to understand this and why this is so important is because as you go, as I was looking at the statistics, the year-on-year growth of production, there was multiple years where production would increase or decrease by plus or minus 20 to 50%. Why is that important? Well, a that means that they have a very volatile production. When you have volatile production, i.e., going up and down in terms of it's still growing up and up and up, but it's dropping for some years and expanding in other years, that's very volatile. It's very difficult to get an estimate for both people who are interested in the markets, who are interested in commodities, insurance, to know like, okay, like, next year it's going to be like this much, or, it's going to be like around here. If you don't know that, then the market goes crazy. Prices fluctuate very intensely, and this plays a lot into food security and things of that nature. So it's important to really be able to kind of nail in on this. And this is only more so ever since the war because there's now no statistics. So this work has only become more important since then. And so what we were seeing is like, for a year it would expand north, and then it would drop down, expand, drop, expand, drop, expand, drop, going more northern, more southern. And so we really wanted to kind of quantify these numbers, and this is how you do it. Okay, now real quick before we get into the results from this analysis. So this is my main job, and I label. I'm a very good labeler. And I probably labeled 100,000, 200,000 cropland points of all different kinds of crops in my life. But this is what it looks like. So when we do this sampling, right, all these little dots, we get a time series of them, of that dot for 8 years, 2001, 2004, 2017, 2020, because we want to label it to then get our actual area estimations and then get our change in cropland. And this is what it looks like. So again, we have that fall planting. Usually because this snow wasn't covering it, it would kind of drop a little bit, but in this case, snow wasn't covering it, so you could still see the NDVI. And then we have the very, very quick rise, and then the the spring senescence, and then harvest for winter wheat. And this is just Modus and Sentinel-2 for extra validation. All right, so let's get into see what's going on here. So for this wheat superhighway, we had where 90% of the winter cropland is used for winter wheat production. We have intensification in the south, i.e., they are growing at faster and higher rates of cycling in the south. So instead of growing one winter cropland every 4 years, they're growing three or four. And then in the north, we have expansion. So they're moving into new lands for growing winter wheat. And these are the 5 largest regions for growing wheat in the country as well. And then if you take that information, if you take those points that we created and take those pixels from the stacking, you can even look at it. It's almost a perfect, not perfect, but it is very, very correlated with latitude, right? So you can see we have intensification. Um, it it increases in the south, right? And you can see like that drop off point where it starts to get curved for intensification. And then for cropland gain, it you can see how it's as you move more north and have a higher latitude, we have higher cropland gain. And another interesting thing too, so we have cropland loss and crop and intensity. Intensity loss is almost flat, and cropland loss is a little bit curved to the right. And why is that interesting? Is because just like when I was talking about volatility, right? As they move north, right, they're expanding more cropland. They are, thinking about the farmer decision making, which is very important. They're making an informed guess, like maybe this year I'll plant. Maybe this year the climate will be good enough for me to plant. And sometimes it works, sometimes it doesn't. And you have cropland loss when it doesn't work, right? But for all intents and purposes, they are expanding northwards and intensifying their cycle of growing in the south. Now, how do you use all this for intraseasonal forecasting? Well, so if we can create something called a winter cropland. You made it up, but called winter cropland use ratio, i.e., how much is each pixel of cropland being used for growing winter wheat on a 4-year cycle? And this is how you create your capacities, i.e., what is the then future growth of this, of if they were to continue at further intensifying their cycle of winter cropland growing, how much more could they get? And so if you use a winter cropland use ratio of 2, i.e., in a 4-year cycle, you grow winter cropland twice. In 2001 to 2004, they were still around 1 or 0.5 to 1, i.e., in a 4-year cycle, they're growing at once. But they're still approaching in the 2017, 2020 interval, they're still approaching and have not yet reached a cycle of 2. And 2 is a pretty, like if you look at for example, the European Common Agricultural Policy, i.e. CAP, 2 is kind of the recommended most that you should do, i.e., I plant 1 year, I let the ground go fallow. The next year, I plant the next year, winter cropland, I let it go fallow. So if they haven't even reached 2 yet, and if they did, then what we can make an educated forecast is that if this cycle continues and we see no reason why it hasn't stopped, then this entire region, which is, not the entirety of Russia, but is still a significant portion, this entire region can almost double still from its 2020 numbers, double its capacity for growing winter wheat. Um, and match the rest of the country's production of wheat production. So there's still, from what we learned from all of this, is that there's still huge capacity for growth, for intensification and expansion. Not expansion, but intensification or increasing that cycle of growth. And it's not without, it's not outside of the bounds of reality for them to do that. So they still have 69% capacity remaining for growth. So yeah, just real quick, just to go over some numbers that we learned from all of this stuff using these maps. We have a 40% change in land cover land use due to winter cropland growth. 40%. That's accounting for all land, including outside of agricultural land, which is huge in a place like Russia. 29% of that growth, of that change, was due to winter cropland growth, i.e. expansion and intensification. We have a latitudinally dichotomous growth. So we have northern expansion, southern intensification. And based off of our winter cropland use ratios, we have a 69% capacity remaining for continued intensification of existing winter cropland. So we still expect to see like that continued growth. And this paper was published in Remote Sensing Applications. If you guys are interested, you can go check it out, read it, see how we did everything there. And so that's it for me. If you have any questions, thank you so much for being here. And thank you to Waleed for hosting me.
Thank you so much, Christian. It's super cool to see this work like so nicely presented. I always come to you, ask you so many questions about what you do, and now you're answering me, very clearly. Open the floor for the questions. Please share any question if you have, and of course the panelists also, if you have any questions, go ahead. I would just to know, like, I know that people don't maybe realize, but like to make a map, Christian, like
Mhm.
for that oblast that you made, of like how much time it take. That's my idea. I want
Yeah,
to just like to see how much
it's a good
effort it
question.
take from
It's a good
from your side.
question. So there's many steps to making something like this on the right, for example. Well, let's start with the left. Left with Modis, pretty fast, about 30 minutes if for the entirety of Russia. If you have the data and everything else cleaned and organized, literally running the GMM program that I have, about 30 or so minutes for the entirety of Russia. You probably can get that cut down a little bit because I do lots of transformations and things and little
Mm,
fancy things in it to make it better. On the right, however, with an LSTM, it's entirely dependent upon your GPU, your access to compute power, and yeah, to your compute power really. So with the current clusters that we have at UMD, I can do this 10 meter using Sentinel-1 and with, again, because what I do is I add more features to it at every 2 week or 1 week interval. And when you add more features, it takes longer. But around 12 features, which is 12 time steps, 12 composites, it'll take about 4 hours or so. Now, I never really optimized it to to be fast, right? This was for research, and I was like, okay, let's just get it done. If you optimize it, you could get it broken down and you can use things like quantization. So quantization is where you reduce your data type and your data bits down from floats to bytes, and that would make it faster. I don't know what for this specific case what that would be. Maybe I don't know, but it would be much faster. So it does take a lot of time. The real time consuming tasks though is that once you make all this, you have to validate it, which is like, going through points and being like, is this right, wrong, right, wrong, right, right, right? Mostly, hopefully, right, right, right. But
mhm.
yeah, you get the point. So that's the real task behind this. But it does make very nice maps. That's a
All
good
right, cool,
question.
cool.
Yeah.
Yeah, the computing is not the problem, but your expertise and sitting down and like looking at every point, I think that what
Yeah.
take months.
It can take a long time depending upon and when you listen to and tomorrow with Sergey when he gives his presentation, I'll get a lot more into the math behind the expected accuracies based off of the samples that you want to throw to validate a map, which is like the most important thing here.
Excellent.
So, Nick,
Thank you, Christian. I don't know if you have access to the Q&A
yes, let me
box.
take a look.
Yeah, you have
Oh
two
yeah, we have
questions
two.
there. Yeah, perfect.
Okay, let's go with Christopher first. So, on the use of break crops to potentially push the wind even higher. Yes. The climate change on fertilization and subsequent yields. Yes. Very good question. All right. So Christopher's question is about using cover crops to increase the winter cropland use ratio, and also what are the changes of yield along the gradient. Very good question. And there's a couple of new, and you're going to hate me because it's nuanced. But for the second one, for the first one though, what we are seeing is in the south regions, and let me pull up, this is a good one. Let me pull this up. So in the southern regions, which is Stavropol, or let me get to winter cropland use ratio, which is, yeah, Stavropol, Krasnodar, and parts of Rostov, or yes, Stavropol and Krasnodar. Let's focus on 2017, 2020. So that's down here. This is the best conditions, are the best regions for growing this kind of type of winter wheat. And they actually have a higher winter cropland use ratio, higher than 2. Um, they use heavy amounts of fertilizers and inputs for this particular region because they have access to it. They have lots of gas down there. For cover cropping, they do cover cropping in Russia, but their information related to it, i.e., their statistics. So then what I can then take that information and then translate it to, okay, does cover cropping lead to a higher yield in this part of the area? My informed guess is yes, they do. And they do that kind of cover cropping to increase it, but it's not as a widespread practice in new areas. I want to be very lawyery about this though, because I can't say for sure because it's difficult to, or not difficult, you can do it, but without the lack of ground truth information, I would love to build a cover cropping map of this area, but it's difficult to then to do it at scale. You could do it on a small scale, but it's difficult to do it at scale to really see. But they do have high amounts of fertilizer input. The one thing though that about ingesting that data is that Russia produces a lot of their own fertilizers, i.e., I can't go on like a site and get like how much fertilizer did they input or import to then do that. So it's kind of a black box a little bit, but good question. Second question, latitudinal gradients. Hold that thought for Natasha when she gives her talk this afternoon. But more or less, yes, what's going on is in the southern regions, we have a much higher yield than in the northern regions. But Natasha can talk more about that. So I do the areas, Natasha's yield. Okay, next question. Good question. What kind of post-processing do you apply? Because there's no salt and pepper effect in the output. Aha, thank you so much for saying that. Um, so there's no salt and pepper here for two things. One, I have a very, very good agricultural mask. That agricultural mask is made from Potapov, Peter Potapov. If you look him up, you can find all of his maps. He is a professor here at UMD, or he was. And they're also downloadable on Google Earth Engine. Just look up Peter Potapov. I can link it to you. What I do is he has built every 4 years agricultural masks of just cropland for the globe. They're not perfect, but they're very good. And I stack them all together, and then I do a agreeableness proportion. So if it was at least twice it was detected as cropland for 20 years, I take that and I build a unified mask. For and I want to say this is actually kind of important. Be careful, Mohammed, be careful of heavy amounts of post-processing when you build maps for area estimations. Be careful of it. You can do a little bit of sieving, very small, 1 or 2 pixels connectivity at most. Anything more than that, you're risking um, you're risking connecting fields together with a fine spatial resolution, 10 meters or less, where you have trees in the middle of fields that separate fields. You have a chance of mashing them together and marking um, uh, trees or other things that are not cropland if you do a sieve. So be careful of that. I do a tiny bit, but the post-processing mostly, this is actually just, this one isn't even sieved, this specific case. But the post-processing for this is very minimal. It's really just converting it to an Albers equal area projection so that you can get accurate area estimations. So that's a very good question. How do I distinguish winter wheat from other cereals? Ah, very good question. Okay, now we're gonna get into the caveats. So it is possible, said it is possible to distinguish between barley and winter wheat. It is possible, and people have produced papers on this. But the people that have produced papers on this, and I challenge you to find one that doesn't, is they have a ton of ground truth statistics or ground truth data to train a model to say this is barley, this is winter wheat. In our specific case in Russia, we have none of that. Not even for the past 10 years, none of it. And even if you're driving on the side of a road, right, you're just driving and you see winter barley and winter wheat, it's very difficult to tell the difference between the two. So if it's difficult to tell the difference between the two if you're just driving on the road and looking, seeing it from space is even more difficult. How do you do it though? You can use a red edge and near infrared band to detect the differences between barley and winter wheat at a specific stage in their growth in the months of March to in April. I have to double check that, but at around April, you can see there's a spike in red edge in barley. But at scale, where we're trying to get whole country-wide estimates, you could do it. But going back to the pixel counting approach that I talked about, you cannot get area estimations from pure pixel counting. You have to validate it, which leads us to then, okay, we've built our difference, but then how do we then answer, how do I validate and say this is barley, this is winter wheat, when the difference is very, very small? And that will then increase our uncertainty wildly. So how do I do it for this? Well, I do have historical statistics for winter wheat and all other crops in Russia. And I have a coefficient where I say, okay, in this region, in this part of the country, in Russia, I know that historically 93%, 93, and I get down to very small, like 93.215% of this specific region, their winter cropland is winter wheat. So I just do that conversion just simply with a coefficient of multiplying my final number with that number. Yeah, so that's really the answer. It's very difficult to do at scale. At a tiny scale, right? Like some people produce maps and they go, "Oh, we were able to distinguish the two because we have these two farms in California and we had all this ground truth data and we built a model that can distinguish between the two." That's all fine and dandy, but my work is more, I'm more interested in operational forecasting of large areas. And so to do that with barley is difficult. Um, but you can do it though. But you need lots of points on the ground. Let's see what else we got here.
If you go to the chat, you have more questions.
Okay. Oh my God.
Welcome.
Where is,
You can start from
please
Murad.
mention, oh, the parameters. Okay, the input parameters for, okay, let's see. So how can multi-source remote sensing be used to monitor qualify land use in Algeria's desert regions where ground truth is? Yeah, good question. So you can absolutely do it. Just doing it the same way we said before. And Waleed is working on this a lot and he has a lot of good stuff. You need ground truth data. And this is, this is a thing that we have to use. So you can do it without it, right? You make informed guesses. You say you build out NDVI difference thresholds. So for a specific region, for a specific, you have to look at your crop calendar, how they plant and how they harvest. And you will build out okay, when is the drop in NDVI, for example? When is the drop in BRDF? And then you actually will then make a map and then you'll sample it by looking at, uh, you know, downloaded true color imagery, or you just need to go there and sample it yourself, right? So to get real true estimates, and you can absolutely do this in Algeria, is you go there, you collect your data, and you then use all those points for as your input features for training the model. That's the best way to do this. Let's see. Okay. How do you proceed with BRDF corrections as a pre-processing step for Sentinel-2 time series? Loaded question. I will get back to you on that one. But essentially, you are doing a series of normalizations. So you first want to correct for top of atmosphere, which you can get with Sentinel-2 harmonized. I need to look that one up specifically, and I can get back to you on that. And then you want to just do so first top of atmosphere, correct for that. You want, below atmosphere to get the best. You could do it with top, but you know, and then you want to do a series of normalizations. And this is actually important too if you wanted to get more technical about it. I like to do double wise normalizations. What does that mean? You have a composite image of your region. Imagine the entirety of Algeria or the entirety of Russia, like literally the entire composite image for your feature. You then normalize it to 0 to 1 based off at for each band that you want to use. Let's say, for example, you're using true color, so RGB, normalize each one separately. Then you want to, for when, and that pulls apart your values so you can get more separability between your classes. Then when you're doing your classification or your training, you want to normalize again within a smaller area, like a pat, we call it a patch. So you have your total scene-wide normalization. You have that now normalized range of values for your entire scene. Then when you go for training and fitting, training and inferencing, you have like a 500 by 500 pixel block, and then you just normalize the values again at, but not at the individual band level, but just max and min of all bands that you're using. If you're doing true color, it's different if you're doing using other values, but at true color. So then you have even more, you pull apart your values that you're using for inference even more. So imagine it like you just want to keep on, separating out your input features as much as not as much as possible, but you want to just pull them apart more so that you can get more separability, so that the model itself that you're training on and inferencing on can then easily distinguish between those things. There's a lot of different techniques and things. I know some people would say different, but that's what I do, and I find to work the best. Um, let's see, did I get everything?
You missed one question at 9:47 from Muhammad Fahad.
Oh, yes. Good question. Yes, 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 yes. All right, let's get into that. I like that question. So, where are we? Actually, this one, yeah. I have a better, let me, I have a really good slide on this, but I'll just say it. So, Mohammed's asking which input parameters were used for training of the LSTM. Is there any preprocessing required to synchronize Sentinel-1 and 2 data? Good question. So, for the LSTM, long short-term memory model, and for people who don't know, it's a model that's been optimized for time series mapping, time series classifications. And so what it does is it has nodes, right? And it literally will think the model is trained to think that as your feature input is in sequential order, right? So you would start, feature one is the beginning of your harvest season or your planting season. And then as you move forward, you're gunning to your harvest season at the last node. So you want to order for an MLP, you don't care. But for an LSTM, you want to order your features in order, starting with 0. Feature 0 is the first composite, moving forward, last composite. The pre-processing for your Sentinel-1 and Sentinel-2 data, it's you as long as it's in the same data type, it needs to be in the same data type for the model to train, right? So float 32 or byte or however. But really just think about it simply. So you just have Sentinel-1 data, you can do VVVH ratio with, and then you have your Sentinel-2 information. It could be NDVI or it could be true color, your 3 bands. And so the shape of it would be 4, um, followed by your the extent of, or sorry, followed by the feature time period. So 2, for example, if it's the second period of your composite, and then followed by the features that you have for that thing, for your thing. That's what the matrix looks like. I can very quickly just if you give me 1 second, let me just pull that up. I have it right here. Hold on. Right here. Can we all see my screen?
Yes, we do. Go ahead.
It looks like this. So you have your, for example, this is the MLP on the top, and then the long short-term memory model on the bottom. This is what the general architecture of what the both models look like. So we have T1 is the beginning of the feature or beginning of the season, and then T20 is the ending of it, or i.e. T20 is all of your features. T1 is just a single grouping of your features. And then you feed them in like so, and to then get your predicted class of winter cropland or not. I hope that answers your question. I know it's a bit uh, broad of an answer, but synchronizing it, there's lots of papers on how to synchronize Sentinel-1 and 2. Honestly, as long as they're in the same data type, and as long as you're normalizing them differently, don't normalize them together. So like, don't take the min of VVVH and the max of, the red edge or your red, green, blue and normalize them like that. I would say normalize them separately if you're doing double wise normalization. Um, so do it separately and then still normalize them and move forward with the prediction or with the inferencing and fitting. But yeah, you can also, if you want, and you can also look at my paper, I kind of go more into it as well. But for my specific case, actually, it was just with Sentinel-1, but I have done Sentinel-1 and 2 before as well. So
Well, just try to pull up your paper.
yeah,
Yeah, I just put the paper here. So thank you so much,
yeah,
Christian.
thank you guys. This is
That was incredible, and thank you so much for the in-depth and like engagement. That's so
Yeah,
cool.
no,
So cool.
it was great. Yeah, I hope to see you guys. If anyone's interested, please reach out to me. You can
Mhm.
find me on LinkedIn, or I'm sure Waleed will help. Just you can email me. I'm free. We can have a FaceTime or video call if you guys want to talk. And please, yeah, thank you so much. Really appreciate it. And thank you for
And
the great questions.
Christian will be also in the AGU. I don't know if
Yeah,
any one of you will be in New Orleans by December. Christian will be giving a presentation, and yeah. So thank you so much. So now we know the area. Let's see about yield. In
yeah,
we will go back at we'll take a break for like 30 minutes and start again around 10:30 to work with the colleague of us, Natasha, that she was here, but she will come back later at 10:30 to tell us more about the yield. And please remember that we will have also um, what Christian is showing in terms of like science and in science and the research setting. We will show it by the end of the sessions today in an operational and industrial kind of setting. So see you later in like 30 minutes. Yeah. Thank you.
you
Thank you again,
guys.
Christian. Thank you.
Thank you.
And the record will be made available by the end of the sessions. So just the time of like, cutting it, making it look nice and sharing it with you all. Thank you. Thank you. Thank you, Christian, again.